Well, hello everyone, and welcome to our channel 361 Physics. And here we are presenting the first video related with capacitor. And this is part 1. That's why we have to discuss some formulation and basic properties and features of capacitor. So let us begin. Okay, so in first point I have mentioned here the definition of capacitor. As we know that capacitor are the devices which can store charge, and the charge will be stored in the form of energy which is known as electric potential energy. Yeah, and in next point I have mentioned about the uh, capacitance. Okay, and capacitance can be defined as the property of holding of charge by any capacitor. Okay, there is a kind of relation uh, regarding the amount of charge and potential difference between two plates. We know that uh, for capacitor or in general, as we add charge on any plate, and if we try to move another plate nearby to previous or first plate, then of course they develop an electric field. And also due to this electric field there will be a kind of potential difference, because electric field equal to B by D, we know that. So as we increase the amount of charge on the plate of a capacitor, then of course that will enhance or increase the amount of potential difference. Okay, from this discussion we can conclude that potential difference is directly proportional with the charge on any plate of capacitor. Okay, so from this we can write this particular expression. Here I have mentioned uh, I have replaced this proportionality symbol by this C, and this is known as the capacitance of the capacitor, and it can be written as Q by C. If we take potential to be 1 volt, then capacitance of a capacitor is numerically equal to the uh, amount of charge stored in in the capacitor. Okay, so this is all about the capacitance. Now we are going to discuss about the unit, and there are uh, two kind of unit related with the capacitance of a capacitor. One is coulomb per volt, and another in general and mostly used unit is farad. And there are several small unit like microfarad. This is equal to 10 power minus 6 farad. And then millifarad. Okay, this is equal to 10 power minus 3 farad. And of course nanofarad, this is equal to 10 power minus 9 farad. And another one is picofarad. Okay, so this is represented as small p capital F, picofarad, which is equal to 10 power minus 12 F. Okay, so these are some small unit of capacitance. Well, this is about the unit of capacitance. Now we are going to discuss about the dimension. Okay, so here I am going to derive the value of uh, dimension for this capacitance. So as we know that capacitance equal to charge per unit potential. So here I am going to solve the dimension for potential. So we know that potential equal to work done per unit charge. Okay, so and the dimension of work done is ml square t minus 2. Just we have here multiplied the force with the distance. Okay, and the dimension of charge equal to a, which represent the ampere dimension of current, and t. Okay, on solving this we can get the dimension of potential as m l 2 t minus 3 and a minus 1. This is the dimension of potential. And if we put the dimension of potential here, then we can get the dimension of capacitance as this is the dimension of charge, which is equal to the product of current and time. That's why we can easily write here A times T, and the dimension of potential is ML2 T minus 3 and A minus 1. Okay, so on solving, we can get the expression for dimension as M minus 1, okay, and L minus 2 T 4 and A 2. This is the dimension of capacitance. Okay. Okay, now we are going to discuss about the parallel plate capacitor. As we know that the parallel plate capacitor consists of two parallel plates which are separated by a particular distance d, and its area is supposed to be A, and um, the space between these two plates, if it is filled by air, then we can use the expression of capacitance as C equals to epsilon naught A by D. And if the space between these two plates is replaced by another substance having dielectric constant K, then we can use the expression for capacitance as epsilon naught times K A by D. Okay, and if we take the ratio of these two expressions, then we can get this kind of relation, and from this relation we can conclude that if we insert any dielectric medium in between two plates of a parallel plate capacitor, then the capacitance of the capacitor will increased by k times. Okay, so this is the conclusion that we can get from this particular expression. Okay, so this is all about parallel plate capacitor. Now we are heading towards another topic, and this is a special kind of uh, special cases, we can say that. So in this case, two different dielectric are inserted between two plates of a capacitor, and the separation of the two plates is previously uh, is supposed to be D, and the material which are being inserted in between these two plates uh, have the dielectric values as K1 and K2. Okay, so if we think about this configuration, we can easily say that this kind of configuration represents the series combination of capacitor. This is one kind of capacitor, and up to here it will behave another kind of capacitor. Okay, so uh, we are going to use here the relation for equivalent capacitance for the series combination of capacitor, which is equal to 1 by C equivalent equal to 1 by C1 plus 1 by C2. And now the separation between uh, this capacitor becomes D by 2 for first capacitor and D by 2 for another capacitor. That's why for in this place, in the place of C1, we can write here epsilon not A by D by 2, and for C2 in the same way we can write epsilon naught A D by 2. Okay, on using these two value here, we can get this kind of expression, which is the direct relation for the capacitor which has two kind of um, dielectric substances inserted between uh, two plates of it in series combination. Okay, now we are going to discuss another case when the dielectric are placed in this particular form. That means when the dielectric are placed in sideways. Okay, so in this condition we can suppose the capacitor are in parallel combination, because in parallel combination, we know that suppose these and these two are capacitor which are in parallel combination, so just we have to connect these two plates by a wire. Okay, which means that these two plates are connected and these two plates are connected with each other. So in the same way, we can suppose this and this point, in this point these two plates are connected with each other, and that's why we can say that this capacitor, there are two capacitor which are connected in parallel combination. And in previous case, when the plates, uh, the region in between two plates were empty, uh, in that case the area of the plate is supposed to be A. Then now we can suppose the area of capacitor is divided into two equal parts. Okay, and that's why we can suppose the area of each part to be A by 2. That means half of the initial area. So as I have mentioned that in this condition, the plates, the capacitor are supposed to be connected in parallel combination. That's why the equivalent capacitance uh, can be expressed as the sum of individual capacitance of individual capacitor. And on solving uh, the expression by using C1 equals to epsilon naught A by 2 by D and C2 equals to epsilon naught A by 2 by D, we can get this kind of expression. Okay, so that is all about the uh, combination of capacitor and their special cases. Well, another topic is energy stored in a capacitor and energy density. So uh, as we know that if the uh, plates of capacitor is connected with a battery or with a source, then the battery has to do some work to add the additional charge on the plate of a capacitor. Okay, that's why this kind of work is stored in between these two plates of the capacitor as electric potential energy. So that is known as electric potential energy. Okay, so we can say that the work done by the battery to store or to deliver charge to the capacitor is stored in the form of electric potential energy. And there are three type of expression for electric potential energy. One is half CV square, which is in terms of capacitance and potential difference. Another is half QV square, sorry, not b square, qb, and another is half q square by 2c. Okay, so this is the expression for energy stored in a capacitor, and this is energy density. This is the expression for energy density. It is represented by small u. Okay, so small u equal to half epsilon naught e square, which means that energy density also depends upon two parameters. One is the nature of medium in between two plates, and another is electric field. Okay, so this is all about the energy density. And one thing we have to know from this expression, U equals to half QV, is that on delivering charge by a battery, the work done by the battery must be equal to QV. Okay, if the potential of the battery is V. But energy stored in the capacitor is half QV, which means that the total work done or energy supplied by the battery is uh, is wastage in the form of heat during charging process. And the amount of energy which is get wasted is uh, exactly half of the work done. If we can see here, work done or energy supplied by the battery is equal to QV, but the energy stored in the capacitor is exactly half of this particular value. That's why we can conclude that there is some some amount of energy loss while charging the capacitor by any external source. Okay, so this is all about the energy stored in capacitor and energy density. Well, this first part of the video, that's why we are going to discuss some MCQ questions, and in next part there are several discussion remains to be discussed. uh, so we are going to discuss about remaining terms in next videos. Now we are going to uh, solve some MCQ questions. So let's begin with question number 1. The plate of a parallel plate capacitor are kept at a constant voltage when the medium between the plates is changed from air to dielectric material. The electric field decreases, vanishes, increases, does not changes. Well, so we can solve it as by using the concept of uh, dielectric, or by using the concept of electric field. So suppose uh, this is a model of parallel plate capacitor, and initially the electric field uh, which is, sorry, let me drop this portion. Okay, the electric field which is set up in between this plate, uh, suppose this plate to be positive and this plate to be negative. In the absence of dielectric, the electric field which is set up is acting from positive plate to the negative plate. Okay, now suppose we have inserted a dielectric material, and the due to the presence of electric field, the dielectric material or the molecule of dielectric material so the dipole moment, which means that the polarity or the face which is nearer to this positive plate of a capacitor get negative charge, and the face of the dielectric which is near to this uh, particular negative plate will get positive charge, which means that here will be the concentration of positive charge and here will be the concentration of negative charge. Okay, due to the displacement of the um, poles, or we can say that due to the dipole nature of the molecule of dielectric. Okay, so inside the dielectric we can observe there will be a kind of electric field which is set up inside the dielectric, and this electric field try to reduce the electric field applied by the source. Okay, so net electric field will be E minus E naught. If that means the original electric field will reduced or decrease when we insert any dielectric medium in between any parallel plate capacitor. So its correct answer will be decrease. Okay, so this is all about the first question. Now we are going to solve another question. Question number 2. Unequal capacitors are first connected in series, okay, and then in parallel. The ratio of maximum to minimum capacitance is. One thing we have to know that when we connect capacitor in series and capacitor in parallel, then in series combination the equivalent capacitor is the reciprocal sum of their reciprocal capacitance. That means 1 by C equals to, okay, let me draw this. Okay, 1 by C equals to 1 by C1 plus 1 by C2 and so on. And if you connect the capacitor in parallel combination, their equivalent capacitance will be direct sum of individual capacitance uh, of the circuit. Okay, so this is equivalent capacitance of parallel combination, and this is series combination. So from this discussion, we are clear that when we connect the capacitor in series combination, then equivalent capacitance will reduce, and when we connect the capacitor in parallel combination, then equivalent capacitance will of course increases. So indirectly, the question mentioned here, we have to find the ratio of the equivalent capacitance of series to the equivalent capacitance equivalent capacitance of parallel combination to the equivalent capacitance of series combination. That's why we are going to solve it as, first of all, we have to find the equivalent capacitance is series combination. So here is mentioned that number of capacitor is n, that's why we can write easily n times c. And for parallel combination, 1 by c equal to 1 by C1, C2, 1 by C2, 1 by C3, 1 by dot 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 plus 1 by Cn. So this is up to n. That means we are going to add n number of 1. That will make here n. And equal capacitance. Suppose this is equivalent, and this one adds dash, and this one adds double dash. Okay. So from here we can find the value of C double dash, which is equal to C by N. Okay. Now we have to find the ratio of these two. So C dash by C double dash will make here and C by C by N, which is equal to N square. So our answer is correct option. Question number 3. If a dielectric constant K equals to 5 is put between the plates of a of a charged capacitor, the charge of the capacitor will be. One thing we have to know that the amount of charge contained in any capacitor does not depend on the dielectric medium or nature of the medium, because C equal to CV, okay? Which means that the amount of charge only depends upon the nature of the uh, capacitor and potential difference between two plates of a capacitor. So we can easily write the answer is Q. That means the amount of charge remains as it is. Now we are moving towards question number 4. The equivalent capacitance of the following circuit is. So it can be easily solved as these two are in parallel combination. So its equivalent will be 1.5 plus 1.5 will be 3 microfarad. Okay, and after solving this, we have to assume here a single capacitor having the value 3 microfarad, and then we have to imagine this combination as the series combination of 3 microfarad capacitor. Okay, so the equivalent capacitance will be 1 by C equal to 1 by 3 plus 1 by 3 plus 1 by 3, which means that 3 by 3, that is 3. uh, it will cancel out, here will be 3 1 microfarad, so C will be equal to 1 microfarad. So option A is again correct option. Okay, now we are here in question number 5. An infinite number of capacitors of capacitance C, 2C, 4C, 8C, 16C, and 32C are connected in series. The equivalent capacitance of arrangement between A and B is. Okay, so connection is in series. So for series combination, as we know that for series combination, the equivalent capacitance can be written as 1 by C1, that is C. Suppose this to be dash. Okay, another one is 1 by 2C, once again 1 by 4C, 1 by 8C, 1 by 32C, and so on up to infinite number. If you take here 1 by C as a constant, we can common, we can write here 1. This will be 1 by 2, this will be 1 by 4, here will be 1 by 8, 1 by this one is 32, and so on. And if we minutely see here, it will form a series having infinite number of items. That means uh, for this we have one mathematical relation, sum of infinite number of item, which is equal to a by 1 minus r. This is common ratio and this is first term. So we can use this particular relation here, and it will be 1 by c. First number is this one, this is a, and common ratio is equal to half in each cases. We can see it. So first number is a, that means 1. 1 minus 1 by 2, it will be here 2 by c, and that's why c dash will be equal to c by 2. So our answer is option B. Well, this is question number 5. Now we are going to solve question number 6, and this is in another side of this paper. Okay. Well, okay, this is question number 7. Okay, let it be. What is the value of equivalent capacitance for the following combination between P and Q? Area of the plate is A and the separation of successive plate is D. Okay, if you see here, there in first picture, okay, in this first figure, there are two capacitors. You can easily see that. There are two capacitors, and if you suppose the capacitance of this capacitor to be C1 and C2, then okay, suppose this to be C1 and its capacitance is C2, then we can easily see here in first figure, okay, here there are um, two capacitor, these two capacitor which are in parallel combination. Okay, that's why we can easily write the equivalent capacitance of capacitor as epsilon naught A by D plus 1 second epsilon naught A by D, which is equal to 2 epsilon naught by D. This is A. Okay, and here if you see here, if you see there, we can find there are three capacitor. See, 1, 2 and 3, and there they are again in parallel combination. So for this we can write epsilon naught A by D. For this one again epsilon naught A by D can be written as, and this can be written as epsilon naught A by D. If we add all of these, we'll get here 3 epsilon naught A by D. That's why we have to find the option which contain these two kind of expression. And okay, in fourth expression, we can get both kind of uh, result. So option D is correct option. Okay, now we are going to solve question number 8, the equivalent capacitance of the combination between A and B. So suppose this is point 1 and this is point 2, and I'm going to take this capacitor here. This is 2, capacitor is C, and this is 1 point. As this point is connected with this side, okay, this side, so this is once again 1, because in wire in generally there is in ideal condition we are going to suppose that the potential difference between the wires is 0. So if this point is 1, then this point will be 1, which means that this capacitor also has two ends which are 1 and 2. So once again we can write here this terminal to be 1 and 2. This is for second capacitor. Okay, now as this point is 2, then this point is again as 2. Okay, because of the previous reason, this is wire, so there is no potential difference between two ends of wire. Okay, so um, again, for this capacitor the ends are 1 and 2. Once again, the ends are 1 and 2. That means these are connected in parallel. That's why the equivalent capacitance is 3C. So option is option C, correct option. Okay, now we are going to solve question number 9. A thin metal plate P is inserted between the plates of a parallel plate capacitor of capacitance C in such a way that its edge touches the two plates, forming Z shape as shown in figure. The capacitance now becomes, okay, so as we know that the two plates are connected by this kind of wire, and after connecting this wire there is no potential difference between these two plates because this behaves as a short circuit. So for capacitance we know that Q by V expression in generally, and as the potential difference is 0, which means that capacitance is infinite. So our option D is correct option. Okay, now we are going to solve question number 10, and most probably it will be last question for this particular video. The total energy stored in the capacitor system shown in figure will be, okay, so this is applied potential and we have to find the potential difference, sorry, not potential difference, we have to find the equivalent capacitance for this kind of figure. Okay, so uh, this is quite easy because if you see here, this 6 microfarad and 3 microfarad is in series combination, and their equivalent capacitance, uh, capacitor, sorry, is in parallel combination with this. So we can suppose this figure as this is supplied uh, potential, and this is 2 microfarad capacitor here, and 6 microfarad which is in series with 3 microfarad as here microfarad, and this is 3 microfarad. Okay, so first of all we have to find here equivalent capacitance for this combination. So as 6 and 3 are in parallel combination, we can write their equivalent as suppose this to be C dash. Okay, so it will be 6 into 3 by 6 plus 3, which is equal to 18 by 9, which is equal to 2. And for this 2, we are going to suppose here 2 microfarad, and these two are in parallel combination. That's why the equivalent capacitance will be 2 plus 2, which is equal to 4 microfarad, and potential is 2. That's why we are going to use here half CV square, which is equal to half into 4 into 2 square, which is equal to 8 microjoule. So our answer is option A. Well, this is all about the first video. We are preparing a lots of video related with different topics. Okay, that's why please stay tuned and subscribe our channel and share our channel so that we can get more and more uh, review regarding our channel. Okay, so please subscribe us and stay tuned. Thank you for watching.